All right, let's get right into it. We all kind of feel like we know what time is, right? It's this constant thing, an arrow just flying straight and true. But what if I told you that our most basic idea of time is, well, it's just not right? What if it could stretch and shrink, and that the very idea of now isn't what you think it is?
So to really get what I'm talking about, let's start with a question that seems pretty simple. How long would it actually take to travel to the nearest star system, Proxima Centauri?
The logical answer, the one we all learned in school, is that since it's 4.24 light years away, if you were traveling at the speed of light, it would take, you guessed it, 4.24 years. It's kind of right there in the name. Seems straightforward. But this is where things start to get really, really weird.
Yeah, as one person on the internet figured out while digging into this, that simple, logical answer, it's not actually correct. The real answer is so much stranger, and it peels back a layer on how our universe actually works.
Okay, so to understand why that answer is wrong, we first have to talk about something we deal with every single second of every day: gravity. Turns out, gravity doesn't just keep your feet on the ground. It literally pulls and warps time itself.
This whole idea has a name. It's called gravitational time dilation. It was first predicted by Albert Einstein, and what it says is that the stronger the gravity you're in, the slower time ticks for you. A clock that's closer to a massive object will literally run slower than a clock that's farther away.
So let's make this a little more real. Imagine we have two perfectly synced atomic clocks. We put one right at sea level, where gravity is just a tiny bit stronger, and we take the other one all the way to the top of Mount Everest, just a bit farther from the Earth's center.
Now, if you could just leave them there for the entire 4.6 billion year history of the Earth, when you came back, the clock on Mount Everest would be about 39 hours ahead of the one at sea level. I'm not kidding. The same amount of time passed for the universe, but it passed at different rates for those two clocks, which also means your head is aging just a little bit faster than your feet. Wild, right?
That Mount Everest example is a pretty small difference, but it's real. So what happens if we take this to an extreme, like a real gravitational extreme? Let's compare the surface of the Earth to its very core, where gravity is just immense. Well, the difference is staggering. That number you just saw, 2.5 years, that's the age difference between the Earth's surface and its core. You heard that right. The center of our planet is literally about 2.5 years younger than the ground we're all walking on. The insane gravity down there has slowed time down so much that it's lost years compared to us up here.
And look, this isn't just some fun little thought experiment. It's real, and it affects you every day. The GPS satellites orbiting the Earth are farther away from its gravity, so their clocks run a tiny bit faster than ours. If the engineers didn't build in a correction for this time difference every single day, your phone's GPS would be off by miles. This bizarre effect is a practical part of modern life.
So gravity bends time. But there's something that has an even more powerful effect, and that's speed. And this is where we finally get back to our little trip to Proxima Centauri, and where our common sense about time and travel just completely falls apart.
The key to all this is something called the Lorentz factor. Just think of it like a multiplier, a special number. The faster you go, the bigger this number gets, and the more it messes with time and space from your point of view. And as you get really, really close to the speed of light, this factor just skyrockets.
So, here's the absolute crucial point. For someone back on Earth, a spaceship going to Proxima Centauri takes over 4 years. But for the person on that ship, just look at this. At half the speed of light, the trip already feels shorter. But check this out. At 99%, it feels like just over 7 months. Get up to 99.999% of light speed, and it's less than a week. Push it just a tiny fraction closer, and that 4-year journey takes just 5 hours from the traveler's perspective. Okay, but that's just our closest neighbor star. Let's really think big. What would it be like for our traveler to cross the entire Milky Way galaxy? You know, a journey that would take light itself 100,000 years to make.
At that same speed that got us to Proxima Centauri in under a week, crossing the whole galaxy would take the traveler just 447 years. Now, okay, a human couldn't live that long, but think about it. We just compressed 100,000 years of travel into less than 500.
But what if we could get even closer to that ultimate speed limit? So close it's almost impossible to measure the difference. At that speed, the traveler experiences that 100,000 light-year journey across our entire galaxy in just 14 seconds. While 100,000 years pass on Earth, they would literally see the whole galaxy streak past their window in the time it takes to send a text.
Okay, so we've established that the speed of your personal clock is flexible. It changes depending on gravity and your velocity. But what about the order of things? I mean, surely, if two things happen at the same time, they happen at the same time for everybody, right?
Well, according to Einstein, the answer to that is a hard no. There is no single universal now. The very idea of two events being simultaneous depends completely on who's looking.
Einstein's famous train experiment shows this perfectly. So picture a flash of light going off in the dead center of a moving train car. For someone sitting on the train, the light travels the same distance to the front and the back, so it hits both ends at the exact same moment. They're simultaneous. But now imagine you're standing on the platform, watching this train fly by. From your perspective, the back of the train is moving toward the light pulse and the front of the train is moving away from it. So you see the light hit the back of the train first. The exact same two events are simultaneous for one person and happen at different times for another.
We can actually draw this out on what's called a space-time diagram. Time goes up and space goes across. For the person on the train, there now is just a flat horizontal line. And you can see on that line the light hits the front and back at the same time. Makes sense.
But here's the kicker. For the person on the platform, their motion relative to the train actually tilts their slice of now. It's slanted. And if you follow that slanted line, you can clearly see that from their point of view, the light hits the back of the train at an earlier time than it hits the front. The order of events has literally changed depending on your perspective. So, time slows down with gravity. It compresses with speed, and the order of events can actually change depending on who's watching. So what in the world does this all mean for us and our perception of reality?
Well, it means the universe is running on a set of hidden rules that are just completely against our intuition. Time is not some universal clock ticking the same for everybody. There is no single absolute now that we all share. Your personal reality, your experience of time and space is totally unique, and it's being shaped by your own motion and where you are. And this isn't science fiction. This is just how reality actually works.
And all of this brings us to one last really big question. We build our entire lives around this idea of a shared, steady timeline that just moves forward. But if that very foundation is this flexible, if it can be bent and twisted so dramatically, what are the things that we think are unshakable truths about our reality are really just a matter of perspective?